Hi, I'm Arun. Welcome to the second video on physics in neural network. In this video, we shall see some of the uniqueness of PIN over the traditional methods. So in PIN, we represent the solution as a continuous differentiable function in the form of neural network, which has input x and y, weight and bias. But in case of numerical methods, we know the output in the vector space. That means we have an output in cell center or cell nodal value. It's based on the method what we use. You may claim in finite element methods we can use the state function as a solution. So that could be in some functional space. But in finite element methods, we locally fit on polynomial. So that's not a global function. But in PIN, especially in vanilla PIN, we fit on function over the whole domain. So that's a global function. So that's the uniqueness of PIN. But if you use finite volume or finite difference method, we only know the solution at the grid points where we evaluate. Another uniqueness of PIN is the meshless method. For example, if you do any finite element method, finite volume method, we need the mesh. We not only need the mesh information, but we also need the connectivity information of the mesh. But in case of physics informed neural network, we only need the collocation points. We just need the XY data points on the domain. So let's say if we are doing finite volume method, we may use some unstructured mesh. We need a lot of data. Apart from XY data, we need a lot of other data like vortex information that we call the XY data. We also need the area of the cell, edge length, centroid of the cell, etc. If we are going higher order methods, we need this information of the neighboring cells. So if we go for even higher order methods, we need this similar information for the neighbors of neighboring cells. In addition to that, we also need the information which maps the current cell to the neighboring cell, and we also need the map of neighbors of neighboring cell. Then only we can go for higher order finite element method. Sometimes when even if we pause this information because of certain numerical issues, we may not even get the higher order convergence, which even if we use the higher order schemes on very bad measures. So we have also published and proof why this happened, especially in conservative discretization for higher order methods. And pins are ideal for moving boundary method. Of course, the solution is from axis fluent, not from pin. But this is one futuristic problem can be handled using pin. So of course, there are plenty of improvement required in pin to handle this thing. But traditional methods may require remeshing every time, but in case of pin, that may not be required. So that's the inherent theoretical advantages of the pin over traditional methods. And even we can do the shape optimization using pins. So now we shall try to understand what is a deep neural network and how that is mathematically expressed. As you know, in most of the deep learning application, deep neural network takes some input and it will fix the target and it will benchmark that interpolation function with the target and we make a network. So in this case, xt is the input and which goes to neuron and we have a set of layer of neurons, then it will go to the output layer. So if we solve some Navier-Stokes equation, our inputs are grid points and time information what we provide, and the output is pressure, velocity, etc. So this part we call as the input. In case of pin, those are collocation points. If we are dealing with large languages model, our text are input to the neural network. So these are neurons. These small blocks are neuron, and this is the output, and this is input layer, and this is hidden layer. Now we shall see what is neuron. A neuron is a computational model inspired by the structure and function of the neuron present in our body. So this is how we can mathematically express a neuron. This is a natural neuron which receives the inputs through dendrites, which is processed in the nucleus. Based on the relevance of the information, it will go to the next neuron. Artificial neural network also function in the similar way. It also receives some input, and we will apply some weights and bias to the input. We know most of our solutions are non-linear. We cannot fit anything in the straight line, at least most of the solutions straight line. So we should go to some nonlinear space. To give the nonlinearity, we use activation function. Some of the common activation functions are turn H, ReLU, leaky ReLU, GLU, ZILU, sigmoid, etc. In neural network, we commonly use turn H and sigmoid. Sometimes we may also use ZILU, GLU, and those stuff. Generally, in image processing, we prefer ReLU. If ReLU has some issues, we may go for leaky ReLU and other variants of ReLU. Then it goes to the next neuron or output. So this is the building block of any neural network applications, which is based on pattern recognition or large languages model, etc. Now we shall dig into what's the mathematics behind neural network. So we already saw neural network takes some input. So in physics informed neural network, our input is the collocation points in our domain. And we add some weights and bias to that collocation point what we feel. Then it will form one function. We make a linear combination of these weights and bias to the input and we get this function. So this W1, W2, W3 and B1, B2, B3 are the weights and bias which are free variables. So those values will be found through our optimization algorithms. So this is how we can mathematically express this. So after this, we will feed that information to activation function. In this example, we have taken turn H as the activation function. Once that is completed, we will feed that to the next layer of neurons. So now we shall try to understand this through a curve fitting. Because if you try directly go to physics informed neural network, it may be slightly complicated. Now, let's say we are interested in finding the neural network equation of this curve y is equal to x square. So this is a graphical representation of the y is equal to x square equation. And this is a tabular representation. Before getting into neural network, we shall see some of the other existing curve fitting procedures available. One of the very common curve fitting procedure is Fourier series. Most of you might have studied this Fourier series approximation of your function in your engineering mathematics. So general form of Fourier series representation can be represented like this. Here we have a constant and we have a Fourier and sine basis to fit this function. In Fourier series, we don't use some optimization procedure to calculate this A0 and A0, AN and BN. If I were the one design the Fourier series, I would use that optimization algorithm to calculate it. Unfortunately, or fortunately, it was discovered by Fourier. He's a very clever guy, so he has chosen a better basis. So he has chosen this sine and cos basis, and you can notice that which has the argument n pi. So this makes this function cos 1 pi x is orthogonal to other set of series in the Fourier basis. so that the solution once functional space will not come or interfere with other functional space. That's the advantage of the Fourier series. So because of that, he was able to make a simple formula for this coefficient. Otherwise, we will make a curve. We will make a least square fit to calculate this A1, A2, AN, or and B1, B2, Bn, like that. So that's the quite nasty procedure. The Fourier made it very simple. That's why this series is very famous. So if we fit this equation y is equal to x square, we will get this equation. Let's try to visualize this equation. Here n is the number of Fourier series we will be evaluating. So if we use n is equal to 1, this is not a good fit. But when we use n is equal to 5, it has some issues at the end that x is equal to y location reduces with increasing order. So now we shall see how to approximate this function using neural network. There is no big connection between neural network and Fourier series. But Fourier series is a clever way of doing because neural network was invented in 1990s. We were not that much clever like Fourier. That's why we use some optimization algorithm to calculate the Fourier basis. So here, AN, BN, A naught, and those kind of things are free variables. But in neural network, those weights and bias are free variables. Even we can use Fourier series as a basis to neural network and do the Fourier series. Now we shall approximate this function using the neural network. Here we have taken very simple neural network, which takes X as the input, and we have two new input neurons, and we have one hidden layer. Of course, we will be having one output layer. So in the table you have seen we have several values of collocation points which start from 0 to 1. So first we take x is equal to 0 as an input. So we already saw we will be using linear basis in most of the neural network application. That's what we have written x plus w x plus b. Because we have two neurons that we've taken w11 w21. So both neurons will be having two biases, B1 and B2. So it has taken some random this value. This we call the initialization. So there are plenty of initialization procedures available over the time, over the videos or over the course we shall discuss the effect of the initialization procedure on the solution of the neural network. If we substitute this 0 here, we will be getting this value. After passing that to activation function, we will be getting this value. The output of that will be passed through the next set of neurons. Here we have four connections, so we'll be having three parameters for the base. And this is the output of the first set of neurons. And this is the base, which is a free variable. Once that is over, we'll be getting Z1. That will be feeder to the activation function. Finally, we get this value. So before going to y value, we use a linear operator, which will convert this into a single value. So this is a y predicted value. The total function can be mathematically represented like this. So in matrix form, we can represent like this. So this is how we can visualize the neural network in the mathematical form. So this is pretty simple neural network. That's why we are able to visualize it. But when we go for very complex neural network, which has lot of layers and neurons, this will become very nasty. So once we know this value, when x is equal to 0, the y value is supposed to be 0. But we got around 0.9. This is a wrong value. So that's because we have the initial gates are wrong. So our objective of the optimization algorithm is to find the optimal weights and bias which satisfy this at various points. Here we have tested this at x is equal to 0. Likewise, we will feed x is equal to 0.1, 0.2, and we will summate all the errors and make a single loss function. Most of the cases we will be using mean square error, but there are plenty of loss functions available uh, in various packages like PyTorch, TensorFlow, and others. We will discuss some of the loss functions in the upcoming slides. So here we have taken the mean square error, and once that is over, we will use the gradient-based methods to update our weights and bias. So we shall see how it works in the future video. In some video, I will try explain the backpropagation algorithm and where we will get how this gradient propagate back and correct it over iteration. So now we hope we got a overall idea how mathematics begin on simple neural network, how the neural network optimize it based on the input and target we give.